Okay, hey everybody. So the subject for this video is a supplemental video on what's sometimes called tabular integration by parts or fast integration by parts. So just a super quick review of integration by parts. The formula, we can derive it from the product rule. The derivative of fg is f prime g plus fg prime. And integrating both sides of that, we see that fg equals integral of f prime g plus integral of fg prime. And we typically say that to let u equals f of x, v equals g of x, then du is f prime of x dx, dv is g prime of x dx. And we can rewrite this as uv equals integral of v du plus integral of u dv. And then solving for integral u dv just gives us uv minus integral v du. So that's usually the format that integration by parts is presented in. And we can see effectively what it does is under the integral sign, the u becomes a du and the dv becomes a v. So effectively what we've done is we've moved the derivative from one factor to the other factor. When written this way, we move it from v, the derivative was on v over here, to u, the derivative is on u on the right-hand side. Now, there are some cases where you want to do integration by parts repeatedly. And again, recall that what do we choose for u versus dv? We typically choose something for u or attempt to choose something for u that when we differentiate it once or maybe a few times, it goes to zero. So typically that's a power function. There are other examples of integration by parts where that's not exactly true, but this repeated integration by parts really comes up whenever one of our functions is a power function that we can differentiate and eventually get it down to zero. So repeated integration by parts will denote the nth derivative of u as u to the kind of power, in a sense, to the superscript parentheses n, and repeated integration and integrals of u, or the antiderivative of u, being u with a superscript minus n, parentheses minus n. So these aren't powers in the sense of exponents. They're a notation for the nth derivative, u superscript parentheses n, or for the nth antiderivative, u superscript parentheses negative n. And so if we consider the integral of u times w dx, so here we're writing dv as w times dx. So uw dx under the integral sign, this is how we would, typically see an integral that we want to use integration by parts for. We would see an integral of something times something dx, and we might think, after maybe trying some simpler things like substitution and so on, we might think of using integration by parts for something that looks like this. I note that this is going to be, well, v is the integral of dv. It's the integral of w dx. That's w superscript minus 1. So uv is u times the antiderivative of w minus v du. And again, v is the antiderivative of w, and du is the derivative of u dx, u prime of x dx, or u superscript 1 dx. So we're writing this in maybe a slightly unfamiliar way, because the goal here is to keep track of how many times we anti-differentiate or differentiate a given factor when we repeat this process. Because here we can look at this as an integral of two factors dx, u1 and w minus 1 being the two factors, or uw minus 1 comes over, and then we have minus, and again we want to take a derivative off of w and put it onto u. So in our integral over here, w to the minus 1 becomes w to the minus 2, we took a derivative off of w. In other words, we anti-differentiated w, and we differentiate u, so u picks up a derivative. It goes from u superscript 1 to u superscript 2, second derivative of u. And then again, following this same pattern here, we pick up a factor of derivative of u times the second antiderivative of w. Since this integral was after a minus sign, we get the minus uv term, and then minus a negative or plus the integral term. We can do this again, and we can keep chaining this on for as many terms as we need. And again, if there's some natural number n where the nth derivative of u is 0, then this remaining integral, after we do this a certain number of times, will end up being 0. We'll just be integrating 0 dx, which is just 0. And we can compute this repeated integration by parts quickly. So for example, suppose that the fourth derivative of u is 0. So maybe u is a cubic function, its fourth derivative being 0. Then again, integral of uw dx is u times the antiderivative of w minus u prime times the second antiderivative of w plus u double prime times the third antiderivative of w minus u triple prime times the fourth antiderivative of w plus an integral that will have the fourth derivative of u, but that's just 0. So this integral just goes away. And we can see that there's a pattern here. Going from one term to the next, we switch signs, and we start with u times the integral of w. So if I make a table where I list u and w as the first entries in the first rows, and I'm thinking of the u's going down that column as being differentiated from row to row, and the w's being integrated from row to row. So u turns into u prime, u double prime, u triple prime, and so on, and w turns into integral of w, integral of that, and so on. So if that's the case, then I see that my formula here is, well, u times the antiderivative of w. So I have this kind of diagonal relationship here. I get u times w times the antiderivative of w times w superscript minus 1, and that comes in with a plus sign. My next term is minus u prime second antiderivative of w. So again, I have this multiplication along the diagonal here, comes in with a minus sign, and then a plus, and then a minus, and then I've gotten down to 0, so my next factor is just going to contribute 0. So let's look at two examples. And as an aside, you might ask, where does things like this come up? This comes up when finding moments, whether we're thinking of moments in the sense of things like maybe probability distributions and so on, or like moments in centers of mass. That's where things like this tend to come up, where we have a power of x. Often it's just x or x squared, but it could be a higher moment if we were interested in some other behavior, and then times some function. So this is a candidate for integration by parts because I see that I have the I have an integrand with two factors. One that as I differentiate it goes to 0, and the other that integrating it, I can do that okay, right? I can integrate e to the minus 3x a bunch of times. That's not a problem. It's not something like e to the minus x squared that I would have trouble integrating. And x cubed differentiates and eventually gets to 0. So I want to differentiate x cubed. I want to integrate e to the minus 3x. And if I go down my differentiation column, I have 3x squared for the derivative. 6x, 6, and 0. And integrating e to the negative 3x, that gives me e to the negative 3x times negative 1/3. Then e to the negative 3x times positive 1/9. E to the negative 3x times negative 1/27. I know these are going diagonal whenever I'm going to multiply them, so the 6 needs to pair with the next one down. So I have plus 1/81 e to the negative 3x. And again, these pair off this way with a plus here, a minus, a plus, and a minus. So this integral turns out to be plus x cubed times negative 1/3 e to the negative 3x, and then minus 3x squared times 1/9 e to the negative 3x plus 6x times negative 1/27 e to the negative 3x, and then minus 6 times 1/81 e to the minus 3x. And we can simplify this a little bit. Oops. We can factor out an e to the minus 3x from everything, so that takes care of all of these factors. And I see I have, what, a negative 1/3 x cubed. I have negative 3 times 1/9, or that's a negative 1/3 x squared. I have negative 1/27 times 6x, so that's a minus. The one of the 3's from the 6 cancels with one of the 3's from the 27, so that's minus 2/9x. That takes care of this bit. And then minus 6/81, again, one of the 3's divides out, so that's a minus 2/27. And then just the constant there. So, and I suppose we ought to be proper and put a plus c at the end. Note that, as an aside, note that this constant is multiplied by the exponential. So it's this minus 2/27 is not it's not an actual constant. We need the plus c at the end away from the e to the minus 3x. So, but that's our integration by parts. Obviously doing this step by step, doing a bunch of integration by parts, picking u and dv and so on, would take quite a while. In a second example, say integral from 0 to pi, x squared sine of x over 2 dx. How does having a definite integral affect any of this? Well, we're just going to evaluate this whole thing from a to b. So we could just find our antiderivative and then evaluate each term from a to b. So we'll choose to differentiate the x squared bit and integrate the sine of x over 2 bit. X squared differentiates the 2x to 2 and then 0. Sine of x squared integrates to, well, sine integrates to minus cosine of x over 2. If I were to differentiate this, that would pop out a factor of 1/2, so I need a factor of 2 here to fix that. If I anti-differentiate again, I get a minus 4 sine of x over 2. And then I know that this 2 on the left here needs to pair with the next one down, so I need one more of these. Anti-differentiate again, that gives me a plus 8 cos of x over 2. And again, these pair off this way, plus, minus, plus. So this is equal to the antiderivative minus 2x squared cos of x over 2 minus 2x times minus 4 is plus 8x sine x over 2. And then plus 2 times plus 8 is plus 16 cos x over 2. And we're evaluating that from 0 to pi. Or this is going to be negative 2 pi squared cos of pi over 2 plus 8 pi sine pi over 2 plus 16 cos pi over 2, and then minus this stuff at 0. Well, at 0, we have minus 2 times 0 squared cos of 0. That's just 0. Plus 8 times 0 sine of 0 is 0. Plus 16 cos of 0 is just 16. And we can simplify some of this. Well, cos of pi over 2, right? Remember that cosine goes like this. Here's pi over 2. Cos of pi over 2 is 0, so this zeroes out, as does this. And sine of pi over 2, of course, is just 1. Right? Sine of pi over 2 is 1. So this first bracket just gives me 8 pi times 1. And my second bracket, remember the minus, gives me a minus 16. Right? Again, much quicker than doing this a few times with the u's and the dv's and all of that. So using this tabular method for integration by parts can be helpful in some situations. I want to do all integration by parts this way. Of course, if you only anticipate having to do one step of integration by parts, probably just going to be easier to pick u and dv and go that route. Or if it's a trickier example, something like, integral of e to the x cos of x, where you have to do a couple integration by parts and then solve for the integral. Those would be ones where it's the value in doing these steps is probably minimal, right? It's adding an extra layer of complexity and confusion and probably not saving you a whole lot on the side of the calculations. But for examples like these, I think these are examples where this saves a lot of time and a lot of hassle. And even though we add some complexity in doing this tabular form, we probably reduce complexity a bit overall by not having to do the integration by parts formula several different times. Okay, so that's all for this supplement on tabular integration by parts.